Hello, I'm Kristen Zong, and I'll be presenting the Spearman Rank Correlation Coefficient in the RUNS test. You'll have to forgive my computer. It's kind of like a dinosaur, and it may sound a little loud. There's no additional fans blowing, it's just that loud. So please bear with me, and I hope you can still understand the information that I'm trying to present without being distracted by my loud dinosaur ancient computer. Alrighty. So the Spearman Correlation Coefficient test is a non-parametric test that measures the strength of the relationship between two ordinal variables. It measures the relationship between two variables that are also related, but they're not linear. Here's the formula for the calculation to determine the strength of the relationship of the data set. We will have an example later on in this presentation that will clearly delve into this calculation. The values can range from a positive one to a negative one. A positive one will be a perfect association. If there is a 0, there is no association between the ranks at all. If there is a negative one, it is a perfect negative association. So what does R mean after we have our calculation? Here is kind of a grouping of what each R can mean. You will have a grouping of either very strong, strong, moderate, weak, or very weak. Obviously, if you're trying to find a strong relationship between the data set, you want an R value of 0.8 to 1, or as close to it as you can. When we are plotting our data set, we will get graphs, and they'll be depicted in a monotonic relationship. A monotonic relationship, it's an important assumption of the Spearman rank correlation test. It is important to recognize that these relationships are less restrictive than a linear relationship. So as you see in the first two graphs, the first graph is more linear and the second graph is not as linear, but it still has kind of a linear flow. The far right graph is that non-monotonic graph. Later on in this presentation, we will see a graph that looks more so like the middle graph. There is still that positive relationship, even though it's not a perfect linear relationship, because that's not what this non-parametric test is depicting. It's not depicting a linear relationship, it's depicting the relationships between the data. With these graphs, we'll see as one value increases, so does the other value. And you can also see that one value may increase and the other value may decrease, and that's how you get the shape of these values. So here's our example. We have not used this example this semester. It was found online, and we wanted to determine the relationship of test scores between the 6th grade English and math class. So you first must state the hypothesis. The hypothesis is that there is no association between the English and math scores. Our alternate hypothesis is that there is an association between English and math scores. So here's our data set. I know that might be a little hard to see, so I will zoom in a little bit. Just bear with me here for a second. We'll just pretend that these lovely 6th graders didn't study that well the night before this test, because these are kind of low scores. There are 10 data sets, and you should have an even data set for each group. So here's what we must first do is rank the scores. We have to rank each score separately. You place a 1 with the highest value, and the lowest score gets the highest rank. So here in our example, we have 10 scores, our 10 data sets. Our lowest test score will get the highest rank. So you see in English, this 6th grader scored a 45, so they will get the highest score of a rank of a 10. The student who scored the 80, which is the highest test score in this data set, will receive a rank of a 1. I hope you can see that there are 261 in this data set, and so we must take the average of the ranking of these two, which happen to fall in the 6 and 7 ranking. We have no idea which one is actually 6 and which one is actually 7, so you have to give them the average of the two. We do the same thing with the math scores. Our lowest test score is that 40, so it gets the rank of the highest score, a 10, and our highest test score is a 77, so it will get the lowest rank of a 1. I know it can kind of be confusing, but if you work through this data again, you will understand how you get the rankings. Step 3, we must find the differences of our ranks. So you can see here, with the first score, you have a rank of 9 for English and 4 for math. The difference will be a 5. You'll leave all the integers in a positive number, because in the next step we will square everything, and even if you were to square -3 times a -3, or multiply a -3 times a -3, you would still get a positive 9. So we're just going to go ahead and leave everything positive. The fourth step is to square our differences, which we did in this last column, and all we did again is just square the difference of the ranks. The fifth step is to find the sum of the squares. I'll go ahead and back out a little bit now so we can see the whole screen, even though there's not data below, but this way you can see the full screen. Here, all I did was just add up every integer that was in the squared data to get the sum of our squares. The sixth step is just to substitute the data into the formula. We use the difference in ranks, which was the sum of the difference in ranks. That gives us our 54. There were 10 test scores, so we plug our 10 into the number of data pairs, and then you finish calculating the formula. In this example, it turns out that our R is a 0.67. So now that we have that data, we want to know exactly what it means. So we'll go ahead and flip back to the previous slide of what does R mean. And you can find it within this grouping. And so we know that this is a strong relationship, a strong correlation between with this formula and with this data set. So since we know what our R value is, we need to interpret the data. So this shows that with an R value of 0.67, it shows a positive, moderate, strong relationship. The higher your grade in English, the higher your grade in math will be. So we will go ahead and reject the null hypothesis that there is no association between these, because in fact we show that there is a positive association between math and English scores. I also wanted to go ahead and run the SPSS system since we have used this semester, and I wanted to input our data from this example to see what this computer program would actually get and see if my math was correct with what the computer gave us. I will again go ahead and zoom in since these are kind of small numbers. There we go. You will see that the correlation coefficient between math and English is a 0.669. And again, here for English and math, it is a 0.669. When we did our calculations, we got a 0.67, so that is definitely, if you rounded up that 0.669, that would round up to 0.67. So it seems that my math was correct. I also wanted to show the graph of the data. Let me zoom out again. And this is using the SPSS data. We will see that monotonic relationship. It kind of looks like that graph in the middle from the previous example. It definitely shows a positive relationship, and it's not a positive linear, but it is that monotonic flow. Next, I will talk about another non-parametric test. This is called the RUNS test. This helps us to determine if our data is truly random. So it's a succession of identical letters preceded or followed by a different letter or no letter at all, such as the beginning or end of the succession. This test allows statisticians to determine randomness of this non-parametric data. So I'll go ahead and provide an example. Again, this example has not been used this semester. This is one I created on my own. And the coin, I went ahead and to a coin flip. I flipped it 10 times to see if it was actually random. So we must state our null hypothesis, and that hypothesis is that the coin was flipped 10 times and randomly landed on either heads or tails. That is our claim. And our alternate is that the null hypothesis is not true. So we want to see if our claim is true. So first we must determine the number of runs in each sequence. Again, I'd flip this coin 10 times, and the H is labeled. That will be relationship to the heads, and the T is for tails. So I got a heads, 2 tails, a head and a head, 3 tails in a row, a head, and then a tail. You then must determine the run sequence. And so you start out by just, you must stop whenever the sequence changes into a different label. So our first run was just a head. The run 2 is 2 tails. Run 3 is 2 heads. Run 4 is 3 tails. Run 5 is 1 head. And run 6 is 1 tail. So we have a total of 6 runs. Step 3, we must find the critical values, and this is kind of where I just went ahead and just had all of my data organized into one slide, so then I could further figure out this example of if to determine if my null hypothesis is true or not. So there were 6 runs. I flipped the coin 10 times. The alpha is at 0.05. The coin landed on heads 4 times. Coin landed on tails 6 times. And to help determine those critical values, I'm going to look at table M in my textbook. So once I flipped to table M, I went ahead and labeled the 4 times the coin landed on heads as N1. So N1 will equal 4. And N2 is going to be 6, which is in relationship to the tails, since the coin landed on tails 6 times. And N2 will equal 6. I look at table N and I find that my critical values are 2 and 9. So now I must make the decision. Since the number of runs is 6, which falls in between the critical values of 2 and 9, do not reject the null hypothesis, because there's not enough evidence to reject the hypothesis that the coin flip results randomly landed on heads and tails. So with this example, we find that the coin flipped was truly random. I hope this presentation has helped you further understand the Spearman rank correlation coefficient and the runs test. Thank you for your time.